Openora is an open-source iGaming framework. It's headless and it's built around plugins. You don't fork it, you don't clone it, you install it like any other framework. One core package gives you everything an operator needs on day one: login, player accounts, wallet, casino games and lobby, chat, notifications, compliance, CMS and audit logs, and entire back-office API. Every shape in the system is a ZOD schema, so your front end can be fully typed using shared interfaces and types. Every external service, like payments, KYC, game providers, or SMS, sits behind a named adapter. In order to change a vendor, you need to change only one line. You don't need to fork the entire platform. And it's made for AI agents. Every project it creates comes with agent instructions, sub-agents, skills, and an MCP server. So your coding agent can ask the platform what exists instead of guessing. In the next few minutes, I'm going to create a new operator project from scratch. Run the migrations, seed it, start it, and then let Cloud Code build a back-office front end on top of it. First of all, we want to create a clear, empty project using our Openora application generator. You can simply run npm create at Openora at 0.1.0 my-casino. This command generates an empty project with the basic backend setup. Your only job is to add your own frontend and connect it to the API. Now let's go to the created folder and open it in VS Code. Here you can see a few configuration files and folders. For Openora, we picked TypeScript. The main reason is end-to-end type safety. We use ORPC to define the endpoints once. From that same definition, we get typed 10-stack queries and mutations for the front end. The types flow from the API all the way to your UI. If something changes on the backend, the front end stops compiling right away. But that is not the only reason. These days, AI agents are trained mostly on JavaScript and TypeScript, so they work better with it. They make fewer mistakes, understand the types, and follow the contracts instead of guessing. Okay, let's get back to our project. As you can see, it's a typical turborepo setup with an apps/folder, turbo.json, package.json, and other files. Let's look at the top level first. Package.json is the workspace root. It holds the scripts you run day to day, like dev, migrate, and seed, and it pins at Openora/core from npm. Turbo.json tells turborepo how to run those tasks across the workspace, so one pnpm dev starts everything. Then there is docker-compose.yml, which starts Postgres and Redis for the local environment, and .env.example file that you copy to .env, and the usual .git ignore. Now the interesting folders. Right now, apps/ has only one app, API. That is on purpose. Openora is headless, so it provides the backend and leaves the front end to you. In a later video, we will add a second app right here, next to API, for our back-office frontend. You will also see a few files that are all about AI, an entire .rulesync/folder. The problem it solves is simple. Every AI tool wants its instructions in a different place. Claude Code reads claude.md. Copilot reads its own file. Codex reads agents.md, and so on. Let's say you have several developers on the team. Someone uses Codex, someone uses Claude, and someone uses another tool. Without a shared source, you have to duplicate instructions and keep all those files in sync. Instead, we keep one source of truth in .rulesync/dot. This tool generates the tool-specific files from it. You edit a rule once and run pnpm-sync::agents. Every agent file is rebuilt from the canonical rules. Now let's look at what is actually inside. There are 4 parts. First, rules/conventions that agents read and follow while working on your code base. Second, sub-agent lists with jobs. One expert turns a vague idea into requirements, another builds the code, and another runs QA. Third, commands and skills, shortcuts like start, plus longer playbooks for tasks such as adding a feature, creating a plugin, or opening a pull request. And fourth, hooks/deterministic scripts that block agents from doing the wrong thing. Okay, now let's open the apps/API folder. This is the whole backend and it is small. Under src/ you have main.ts, which is the server itself, extensions.config.ts, which is the list of everything that is enabled, and two small scripts, migrate.ts and seed.ts, that set up the database. That is really it. Let's open main.ts and see how little code it takes to boot a full iGaming backend. Let's start with the imports. Main.ts imports create app and load extensions from at openora/core/server. It also imports the contracts for the modules we want to expose: identity, wallet, gaming, lobby, chat, compliance, CMS, notifications, backoffice, IAM, profile, and audit. The important part is compose contract. We compose these module contracts into one typed API contract. We do not write the same endpoint types again in a front-end client. Next, we define the iGaming configuration. This is the application-specific part: the casino name, supported currencies, jurisdictions, blocked countries, limits, and payment provider. The configuration is validated when we create it, so invalid values fail early. Services can also use the same typed configuration through dependency injection. Then we set the extension's config path. This makes the app start reliably even when the command is executed from a different working directory. Finally, Bootstrap calls create app with the loaded plugins, the compose contract, the auth schema, the iGaming config, CORS, and the port. Create app wires the server together, and listen starts the HTTP API. The consumer app owns this small composition layer, while the platform capabilities stay inside the published at Openora/core package. Now let's open extensions.config.ts. This file is the plugin registry. Core Plugins enables the built-in Openora modules. Your own overlays and vendor adapters go after Core, so you can replace a default implementation without editing the platform package. The order matters because the last provider for a dependency injection token wins. That is the main idea of the generated backend: a small explicit application layer around a reusable headless platform. You can keep the core untouched, add your own frontend and plugins, and still get typed contracts from the backend to the UI. Now let's run the project locally. First, copy the example environment file, cp.env.example.env. Start the local infrastructure, docker compose up-d. This starts the Postgres and Redis services that the generated backend uses locally. Next, install the dependencies if you have not done yet. pnpm install, run the database migrations and seed the initial data, pnpm migrate pnpm seed. Now start the development server, pnpm dev. The API is now running locally. Keep this terminal open while we inspect the project. Let's verify that the backend is actually running. First, open the API URL shown in the terminal. Depending on the generated configuration, this is usually http://localhost:3000. You should see the API response or the server's health response. The next useful check is the API documentation or route you configured for the composed contract. Open it in the browser and confirm that the generated modules are available. You can also call an endpoint directly from the terminal. For example, curl http://localhost:3000/health. The exact health path can differ between generated versions, so use the route shown by the server logs if it is different. At this point, we have a running Openora backend, local Postgres and Redis, migrations applied, seed data loaded, and a typed contract that is ready for a front-end client. In the next videos, we will implement the front-end and connect it to this API. We will also build the back-office application next to the API app and use the generated types to keep the front-end and back-end in sync.